Hello, Mrs. Thompson here, and today we're going over Avogadros Principle and gas stoichiometry. Okay, we've talked about Avogadro before, but we haven't talked about his principle, which is what he actually studied. He took a look at gases, and he said, well, if I have three different gases, let's say hydrogen, nitrogen, and oxygen, and I keep them at the same temperature, the same pressure, and the same volume, if I went ahead and I was able to count the number of particles inside, they would all be the same. Okay. This was an idea that he had that none of the other scientists at the time believed. And so he ended up dying without ever knowing that students would learn about Avogadro for a long, long time. Now, what we learned before is how many particles there are in a mole, which is 6.02 times 10 to the 23rd. So scientists had to find that and then credit that to his name much later when they had the capacity to figure out the number of particles. All right, and so if you see this table here, this is just stating I have three different gases. They're all the same temperature. They're all at the same pressure. Okay, but notice they all have different masses. Why do they have different masses? Because for each of them, a mole would mean a different amount of grams. For helium, it's 4 grams per mole. Okay. And then the number of gas molecules are the same. So since that's true, they should have the same volume, which is 12 liters in this case. And I just found that using Pivder. Based on Avogadro's principle, scientists have come up with molar volume. And what they went ahead and did is they said, what if I took 1 mole of gas and I kept it at STP, standard temperature and pressure, 0 degrees Celsius and 1 atmosphere? What would that volume be? And so they measured it. It's 22.4 liters. It doesn't matter which gas you have, as long as you keep those conditions the same. 1 mole of that gas at STP is 22.4 liters. We can use that as a conversion factor, which is great. We say that 1 mole of gas, any gas, is 22.4 liters. There are 2 conditions though. One, which is very important, has to be a gas. Don't ever try to find out the volume of a solid. It won't work this way. Okay. Second, it has to be at STP. As soon as it's not at STP, you do have to use PV equals nRT to find out that information. All right. This is a map. So it's a stoichiometry map that's been expanded to include volume. And so it looks like our stoichiometry map from before, but there's an extra leaf attached, and that's the volume part. Okay, so hopefully you recognize this. So GMMG is what we used to memorize. Now we also can replace that G with an L, which stands for volume. Okay, here's our first example. What volume will 2.5 moles of CO2 gas occupy at STP? Now remember, it has to be a gas and it has to be at STP, or we can't do this problem this way. Okay, our given here is the number with its unit, which is 2.5 moles of CO2, and our unknown is the volume, which the unit for that is liters. And so it's liters of CO2 because it hasn't told me that the substance has changed at all. All right, so CO2 here and CO2 here. Here is that stoichiometry map. Okay, and so let's just see where we're starting. We're starting at moles of CO2, which is here, moles of our given, and it hasn't changed substance. So I'm going to go to the left. We're actually finding the volume of CO2, the given. Okay, so that means I have one step, and I'm using the fact that 1 mole is 22.4 liters. Okay, I'm going to go from moles of given to liters of given. Okay, so let's do that. 2.5 moles of CO2. I'm using the conversion factor. 1 mole of gas is 22.4 liters. I'm going to make that so it's set up for unit cancellation, which would be like that. We'd want the moles on the bottom so that they'd cancel. And so that looks more like this. 1 mole CO2 and 22.4 liters on top. Moles cancel, and you get 56 liters of CO2. That's just with two significant figures. All right, easy. Next one, if 25 grams of ammonia gas is released into a balloon at 1 atmosphere and 273 Kelvin, what volume will it occupy? So the conditions are given here for pressure and temperature, and the reason they're given is so that you know it's at STP. Okay, it's at 1 atmosphere and 273 Kelvin. So our given 25.0 grams of ammonia, our unknown, how many liters still of ammonia? So NH3 and NH3. If we look at that map again, we are starting at grams of the given, which is right here. Remember, the left side is for the given, the right side is for the unknown. And we want to make our way all the way to liters of ammonia. Okay. Now, careful. The unknown is still in terms of ammonia. So I'm going to end up here on this side because it's still liters of the given. So we would go from grams of the given to moles of the given to liters of the given. Careful. So it would look like this. Gram given to mole given to liters of the given. The substance hasn't changed. We didn't need to cross this mole bridge here from one substance to a different substance. Okay, in order to do this, we'd have to want to find a different substance. All right, so let's do that. It's 25 grams of ammonia. When we go from grams to mole, hopefully you remember we need the molar mass. So we're going to add up nitrogen and 3 hydrogens. That's 14.01 and 3.03 altogether. And that's 17.04 when I add the two. 1 mole of ammonia goes on top. Remember, when you're finding the molar mass, it's always for just 1 mole. Okay, grams of ammonia cancel. Now that got me from grams to moles. Now I need to go from moles to liters. Okay, and because it's at STP, I say 1 mole of any gas, which this time it's ammonia, is 22.4 liters. So that cancels. I do the math, and I get 32.9 liters of CO2. All right, here's Pooh. Pooh is filling a balloon with 1.75 liters of helium gas at STP. So it's gas, it's at STP. How many grams of helium did he use? So my given is 1.75 liters of helium. My unknown is grams of helium. And so remember, it's still helium, so it's still technically grams of the given. So let's look at the map. I'm starting here at liters, and I want to go to grams. So to do that, remember it's on the given side. I'm going to go from liters to moles, then from moles to grams. So it would be liters given to mole given to grams of the given. This is a 2-step problem because I'm crossing 1 arrow, 2 arrows here. All right. So 1.75 liters of helium times a conversion factor. Now this time I've got liters here. My first step is to go from liters to moles, so I use 1 mole is 22.4 liters. And I'm going to use it this way, so liters cancel. And then my next step is to go from mole given to grams given. So that looks like this. 1 mole of HE is 4 grams of HE. And that's 0.313 liters of helium. All right, keep going. If 1.25 grams of hydrogen react with oxygen, what volume of oxygen is required at STP? And a reaction is given. So you should notice this is different in that you're changing the substance and you've got a reaction. So you're going to have to cross that mole bridge from mole given to moles of the unknown. So here it is. Our given is 1.25 grams of hydrogen. Our unknown is liter of oxygen. So here we go again. Hydrogen is changing this time into oxygen. Here's that map. We're starting at grams of the given. And we're headed all the way across this time because the substance has changed. We're on liters now of the unknown. That means that I'm going to have to go all the way through these steps, which means we would have grams of given to moles of given to moles of unknown to liters of unknown. Okay, so let's try that. 1.25 grams of hydrogen. I use the molar mass of hydrogen. It's 2.02 in every 1 mole. Grams cancel. I use the mole ratio. Remember, that's the moles of the unknown on top and the moles of the given on bottom. And we use the numbers that are in front. Those come from the balanced equation. So in front of hydrogen is a 2, in front of oxygen is a 1. So there we go. And then 1 mole of oxygen is 22.4 liters because moles of unknown to liters of unknown. We want to find the volume. And that's 6.93 liters of O2. All right, last one. What mass of sodium is required to react with 5.6 liters of oxygen to produce sodium oxide at 0 degrees Celsius and 760 millimeters of mercury? Hopefully you notice that those are still conditions of STP. 0 degrees Celsius and then 1 atmosphere is equal to 760 millimeters of mercury. I do have a balanced equation, which means I will have to go through that mole bridge. It's changing substance. So the given is 5.6 liters of O2. The unknown is grams of sodium. The substance changes. Here's my map. I'm starting at liters, and I'm ending up at grams on the right side, on the unknown side. So that means to get there, I'm going to have to go here first, then here first, which means I'm going from liters of given to moles of given to moles of unknown to grams of unknown. All right. So 5.6 liters of oxygen times, we need 22.4 liters to cancel out those liters, because this is at STP, is equal to 1 mole of oxygen. Cancel out liters of oxygen. Then we have our mole ratio step, because I'm changing from one substance to another, from oxygen to sodium. So 1 mole of oxygen, 4 moles of sodium. Those are just the coefficients from the balanced equation, right there and right there. All right, moles cancel, and my last step is to use the molar mass of sodium, because I'm going from moles of unknown to grams of unknown. And so moles cancel, and I am left with 23 grams of sodium as my final answer. All right, we'll do some practice on this tomorrow. Hopefully this wasn't too difficult. It should be a review of stoichiometry, and we did great on that. So hopefully you will do great on this too.